today. So my name's Andira Schroeder, and I'm the Global Marketing Manager for Link3D. And we're excited to be a part of this America Makes event with Hollers Associates and help bring the community together virtually. So just a few things before we get started. This panel will be interactive. So there's a Q&A tab on the very right here, where you'll be able to ask questions for the panelist, as well as upvote questions that someone else has already asked. And then Terry will incorporate these questions throughout the panel. And typically the ones with the most upvotes do get asked first. So make sure to upvote the ones that you like. And if you are having any technical issues or issues viewing the panel, first things first, try refreshing your page. That solves most issues. But otherwise, for best quality, try to use your computer on Google Chrome rather than a tablet or smartphone, and that tends to work best as well. And if anyone is still having trouble viewing the panel, feel free to direct message me on the chat function in here, and I'll help get you connected. So I will hand it over to John now, if he is up on stage. There you go, John.
Hello, hello. Good morning, everyone. Good morning, Andrea.
Good morning.
So I'm just going to take a couple of quick minutes to welcome everybody. This is now the third of these game day events that we've put on, trying to continue to keep the community engaged and coming together around different individual topics that are of importance. So I really appreciate everyone signing up and taking the time out to participate in this event. We're really excited about the panel, the group that's been brought together, take the discussion. Hey, good morning, Terry.
Good morning, John.
Around, design for additive, but, really talking about the economic side of it and where and how we should be using it and where we're at today, maybe versus where we were yesterday, and where are we going tomorrow. So really excited about the different diverse perspectives that we have, including Stephen Floyd from Northrop is going to be talking. He's actually the lead for our design working group at the Institute. So he's very active in our actual technical working group that is taking on and looking at these different challenges and trying to understand where we're at today, how our portfolio maps to that today, which is critically important for us. That's really the role we're looking to serve in bringing folks together, understanding our current state, identifying the future state, and then really figuring out how do we close those gaps and making sure that we're focused on the right things. So that's what we're trying to do today. This will be a step towards continuing that discussion. Make my quick plug here while I have a couple of minutes. We do have a couple of events coming up here. We have one of our TRXs, our technical reviews and exchanges, coming up in 2 weeks. It's on August 4th and 5th. The intention was that was going to be a face-to-face activity at Ohio State. We've since, we've continued to stay very engaged with Ohio State. They've been really helpful in helping generate content and putting together the program. But ultimately, it's going to be a virtual event. And thanks to Link3D and Ohio State, we've put together quite a program. It's the 4th and 5th. It's 2 half days. It's 12 to 5 Eastern with a networking reception on the night of the 4th. But I strongly encourage folks, there's quite a few announcements that we're going to make. We're going to be talking a fair bit about where we're going as an institute and some very specific opportunities to get engaged. So encourage everyone to pay attention, get registered for that. And then our next game day we've got scheduled already. It's September 10th, and it is going to be focused on the future of additive, so the future of AM. So encourage you guys to take a look at that, and we're really excited to have this panel come together today. So I will hand it over to Terry and let him get started. No mic, Terry.
Thanks, John. Very excited to be a part of this third game day event on the economics, opportunities, and challenges of designing for additive manufacturing. It is the third event. John mentioned the fourth will be July 10th, focused on the future of additive manufacturing. So pencil that into your calendar if you would. We have an excellent group of panelists, and we'll get to them very, very soon. I want to say that if you haven't given this Remo platform a try, if this is your first event using Remo, it's really an impressive, great way to interact virtually. And thanks to Link3D for sponsoring it. I hope that most of you agree that design for additive manufacturing, DFAM, is a critically important topic to discuss. I suppose you wouldn't be here if you didn't agree at some level. I urge all of you to ask questions, offer comments, and really an opportunity to ask three top experts in design for additive. What you'd like to know more about. So John began to introduce the panelists. I'm going to let each of them, they know far more about themselves than I do, although I've gotten to know the three of them not real well. I know Doug Collins is at Avid, just a few miles south of here in Loveland, Colorado. We're in Fort Collins, and so I do get to see Doug once in a while. So Doug, if you'd start, give what's your position at the company, a little bit about Avid, and what do you do? And just 2-3 minutes each, that'd be great.
Sure, absolutely. Thanks, Jerry. Yeah, so my name is Doug Collins. I'm the founder and one of the co-owners of Avid Product Development. I'm a mechanical engineer by degree, and at Avid Product Development, as our name says, we focus on product development, kind of from napkin sketch to manufactured products. And we have a strong backbone and history with mechanical engineering and product design. And so we use a lot of design for additive manufacturing techniques and other traditional techniques as well for designing products. And then on the additive manufacturing side, we focus on production and commercial manufacturing with 3D printing. We have a slew of different technologies, but our focus is with the HP multi-jet fusion for production polymer printing.
Thanks, Doug. Marco?
Thanks, Terry. My name is Marco Quamman. German origin, also based here in Germany. I'm working for Adidas, or Adidas, how you pronounce it, in the US. I'm 13 years now with the company. I'm also a mechanical engineer by trade, and I'm responsible for our 4D program, which is basically our commercial product range for 3D printed products. I'm with the program from the beginning, and since now, I think, 4 years, where we're working with our partner very closely, Carbon, where we're focusing mostly on polymers and photopolymer machines. And I'm basically responsible for the technical side of that program.
Yeah, it's a dinner time in your part of the world, is that right? It
is. And when I told my wife that dinner is postponed to a later time today, she was a little bit surprised, but no worries.
Dinner and maybe a Hefeweizen postponed as well. I happen to have with me one of my products from your company. It's the Futurecraft
Nice.
4D. Yeah, beautiful design. And you worked on this?
Yes, absolutely.
Yeah.
I mean, that was the kind of the second generation of the midsole that we manufactured from that, and really glad to see that it's now basically getting more and more available, and that you're also owning one.
All right, thanks, Marco. Stephen.
Thank you, Terry. Yeah, so I'm with Northrop Grumman, based out of Los Angeles area with our space systems sector. I'm one of our additive manufacturing leads within the company, and I've been involved in additive for 7-8 years now. Been with the company for about 12 years, so my experience there is in all sorts of products across our business areas, from propulsion products to structures products. And right now I lead a team of additive experts and trying to figure out what we're doing with our business for additive.
You work mostly with metals, Stephen?
Metals, polymers, and some other stuff as well.
Okay, good. So if we have questions around metals, you'll be our number one person, and I'll try to back you up. I assume that, Marco, you work mostly with polymers, or maybe entirely. And I know, Doug, you do too at this point. Yeah. Okay, great. So as the first question, and by the way, we prepared several questions, of 4 of us, but I see questions are already starting to come in. We have 2. You can vote on which question you like the best, or questions, and then you'll see a number that moves the question to the top. So it looks like we already have one that has 4 votes and one with 3. I'm going to open up with this question. Why is design for additive manufacturing so important? That's part of the question. And why is it critical, or is it critical in every production case? So you can take both of those questions separately if you'd like. So why is DFAM so important in the context of production, not necessarily for prototyping or modeling, but for production application? And is it critical in every production case? Who'd like to take that?
I can jump in initially if you'd like.
Sure.
So we do a lot of production printing in the polymer space, like I mentioned, and so I think there's definitely a few different reasons why DFAM is so important. It starts with taking advantage of the technology. So if you're going to be using additive manufacturing to produce a product, you really need to ensure that you're taking full advantage of what the technology can offer. If you're going to try just to compete against an injection molded product, there's very little advantage there. So if you can do things like all the things we've been talking about for years of part consolidation, or lightweighting, or textures, or lattice structures, that's taking advantage of the technology in a way that a traditional manufacturing method can't. But from a manufacturing standpoint, where it really gets critical is, especially for a powder bed fusion type technology, is to be able to be really efficient with printing the parts, to be able to nest as many parts as you can in a build, to really help control the economics of the parts and printing them, to really set up, if you're going to be bridge manufacturing or manufacturing that part forever with additive, economics are going to be a driving factor, and we have to be able to compete in that space.
Yeah, so I think there's a misconception among many people who are less familiar with additive for any application, and that is you can just build one at a time and it's really economical. And you're saying there's an economy of scale. In other words, you got to pack that build volume, especially in the case of a powder bed fusion system where you're working with powder. Is that right?
Absolutely, yeah. I mean, it's straight up math. The more parts you can fit in there and still get good parts out, and all of that, the economics just drive. I mean, it's similar to injection molding, right? Cycle time is really important. Well, cycle time in additive is really important as well. It's just different way of thinking about it.
Sure. Marco, Stephen, do you have anything to add?
Yeah, I think this question gets quite an interesting, different dimension when you look at it from a consumer product perspective. Because obviously from a consumer perspective, and that's basically every one of us here, we want to see products that excite you, that have an emotional connection. So there's an aesthetic part to the design of products there that you probably do not have when you're talking about industrial products or industrial production. So we need to make sure that the product from an aesthetic design perspective is really exciting you. And everybody says, hey, 3D printing gives you that ultimate design freedom. But it's the challenge, I think, with design for additive is to be able to incorporate aesthetics, the performance, because you still need to make sure that the product performs. And in the case of a shoe, basically you have very specific boundary conditions to what is from your biomechanics sensible to work. And then the third aspect of it is basically the printability or the efficiency of how you manufacture that part. Because not every process basically has the same set of rules, and we just need to make sure that we tick all those 3 boxes in the end to get a commercially viable product.
And safety, where does that rank?
It's part of the performance aspect of it. So when I say we need to make sure that the product performs, obviously we need to make sure that you don't get injured or hurt while you're running. But that's kind of the part of the overall kind of performance characteristics that we have towards a midsole component. We don't differentiate if it's 3D printed or if it's a foamed or another technology. We have basically the same set of requirements for all our products.
Yeah, I think from a design perspective, that's always going to be, from an industrial product to a consumer product to whatever, you just because you're using additive doesn't change how you approach that from a mechanical or electrical engineering perspective. You still need your factors of safety, you still need to design properly, you still need to test and, do some either FEA or physical testing or both, most likely, to ensure that the products are still designed properly.
That's correct.
Stephen, what are some of the biggest DFAM challenges for building a business case for AM production applications? Can you comment on that?
Yeah, so for building a business case, I mean, a lot of it is coming down to understanding the requirements and how they change with additive or don't change. Right?
Yeah.
And then really getting all the data and supporting evidence that's necessary to maybe prove that that it's not different than the traditional product form you're used to using. And also making sure that you're keeping in mind those DFAM rules that we just talked about in terms of the economics, right? That end of the day, if you're not getting successful prints the first time, that's going to cause more builds, it's going to increase your cost. If you're not respecting the design rules and say you need a lot of support material, that's going to affect your post-processing costs, and at the end of the day, it's really going to start to degrade the business case. So I'm just understanding that the beginning of the design through the print process and what it's going to cost to realize the end product along the way, I think is really the hard part with understanding additive design.
I'm going to dive into the questions. We're getting some good ones here, and we never have enough time to get through all of them. Some questions are better than others, likewise with the ones that we prepared, but this one already has 9 votes, and I think that might be the most we've ever received, including the first 2 events. So to what extent is design for AM a function of the process being used? That is there really one DFAM set of rules?
Maybe I can start with that. No, there certainly is not. It's a really good question because every process, if you're thinking about a photopolymer top-down process that we're using compared to a powder bed process or an FFF, like a filament process, is very, very different and has very different design rules also that not only affect the design for printability, but also the design freedom that you have as a designer to create it. Maybe just an example in a powder bed process where the non-sintered powder is almost kind of supporting the remaining part. You don't have to pay too much attention on kind of supports or a certain set of rules that allows you to print a part rather easily. Whereas in photopolymer processes, it is very, very important to really support a part in a very smart way because you don't have that intrinsic support from the process, and that can lead to significant influence to how you not only design a part but also orient nest a part in the process. So I think every process definitely has their own very specific set of rules.
Yeah.
And I think it's beyond just process as well. I think within each process, you have different materials as well. And that can, tweak even those rules within that technology sometimes. I know in photopolymers, if you're using an elastomeric material versus a harder material, that changes how you approach supporting that part, for instance. Or in powder bed fusion, an elastomeric material again versus a hard material, the gaps between the parts are going to be different, or how you approach orientation might be different. So definitely, I think changes how you think about the DFAM. I think there are some general rules though that you can use everywhere, right? You should eliminate stress concentrators as much as possible. Add fillets. Fillets are almost free all the time. So that kind of thing. Yeah, sure. But there's definitely always going to be some specifics depending on what technology you're going to be printing the part in.
Yeah, I was just going to add that I think there is a subset of rules, if you will, they're kind of similar across the technologies. You're always dealing with gravity for the most part, unless you're printing out in space. But you're generally dealing with gravity, and that leads to either supports or having to account for in your process, and layer slicing. And you're always looking at building up in layers or slices of some sort, shape, or fashion. And so you will find some common rules, I think, across the processes that once you understand it in one, you can sort of abstract to the others. But yeah, when it comes down to the complete set of rules, you really got to understand each process intimately, because photopolymerization is very different than laser sintering at the end of the day.
Suppose you're a small company, and I wish I could get a show of hands because I'm guessing more than half of the people attending this represent a small company. But suppose you're at a small organization wanting to design and manufacture parts by AM. And as you start to peel away the layers, you discover the need to acquire new software tools to help with that. And then you also need to develop Dfam skills before you know whether it makes economic sense. So you have to go down the road a ways and make a time and money investment, software and skills, just to determine whether or not it makes economic sense. How does a small, let's say a very small company, a dozen people or maybe less, overcome this expensive and time-consuming problem?
I think from a design aspect, it all depends what you're trying to do and how far you're trying to take the Dfam component of it. You can use a lot of, very standard CAD tools and general principles for designing, components that are going to be either mass customized or part consolidation or that kind of stuff. That's a SolidWorks, a Pro-E, or whatever, right? So that's a general CAD tool. I think when you start getting into the more complex features, as in lattice structures like Marco's shoes, or you get into surface textures, that kind of stuff. That's where I think more complex and more higher end specific tools for AM really come into play. And you can either then do that in-house to start with, or maybe contract it out to initially learn about it, find out what that right tool is, and then eventually bring that in-house when the time's right.
Yeah, I would double that from a small company's perspective, where you have kind of limited resources. For us, obviously we did it the hard way. So basically, acquiring all these different softwares, we have a very specific requirement, I would say, from a product perspective, and we were really going through it and trying out what worked best for us in order to kind of identify the system we're continuing. But I think the best way probably is to work with maybe one or two prototyping offices that do have a variety of software tools, because not every software tool fits to your specific problem. And then maybe from that experience, take away what the best tool is for your specific product.
And Marco, if I could add to that, not only a prototyping shop, but one that has experience with actual, contract manufacturing, series production.
Absolutely, yeah.
Okay, here's a question that received 9 votes. Do you think that desktop-based printers, such as the Metal X and Studio, have potential for wider adoption in aerospace? So I guess this is for you, Stephen. Desktop metal shop system, for example, being powder-based, does it have a better chance? Are you familiar with those systems, Stephen?
I'm not as familiar with the desktop metals shop system, so I can't really speak to that one. I think in general, to get into aerospace, you're going to have to really prove the quality, reliability, and repeatability of any system. So if they get to the point where the calibration routines and the processes to make sure that the printers are repeatable are in place, I could see anything kind of making its way in, but it's got to meet that bar of quality every time. And a lot of times, the commercial lower cost systems, they just don't have that repeatability to them. Otherwise, they would cost more. So I wouldn't rule it out, but I think it's going to have a harder journey than the systems that are being more invested in from an industrial perspective.
Yeah, I would have to agree with you too, based on my experiences. There's still work that needs to be done, both in the development and the application, and really the qualification process, and to really have that certainty that you can build parts repeatably and to the level of quality required for aerospace applications. Maybe small inexpensive UAVs would be a place to start, and then maybe moving from there.
Yeah, I think we find that in tooling applications or even prototyping applications, that they might find more of a usage in such scenarios, especially if the design goals really represent the more expensive production powder bed style machines. Then you could see some usage for that as well.
I know that companies such as Dfam Metal is initially not going after aerospace and automotive and some other industrial applications. So, aerospace and medical are pretty high bars as far as getting acceptance, adoption within those industries, and so it's probably not a good place to start with those binder jetting type systems. Do you think additives cost will decrease to the point where it will obsolete traditional manufacturing processes such as casting, stampings, and so forth for large volumes? So you think it'll decrease to the point where it will do that?
Very difficult question, I think, to answer in general. I don't see that in the next 5 years probably, but never say never. I mean, the industry is very innovative, and it could very well be that for a very specific application, it does make sense, even at large volumes. I mean, if you remember mascara brushes, for example, that had been 3D printed, it did make sense because it was a lot more complex and more expensive to manufacture them traditionally. But for the majority of products, I doubt that. I think in the next 5 years, I doubt that will happen.
Yeah, and I think it really comes down to the topic of the day is the whole DFAM component, right? The mascara brushes are a perfect example, right? If it's designed properly for that technology, for that specific use case that really takes advantage of the technology, absolutely, it's going to make sense sometimes. For general products, if you're going to have a housing that makes sense to injection mold and you're going to make 10 million of them, yeah, that's a long ways out before additives is going to compete in that space. But I don't think us looking at additive as a replacement technology is really probably the approach that we're taking today, and probably for a long time. I think it's another tool in the toolbox, and you see large manufacturers ramping up additive lines alongside their big production lines so that they can take advantage of the DFAM components for those specific components, but not for the ones that it doesn't make sense. So I think it's another tool in the toolbox more than anything.
Yeah, I think it's exactly that, another tool in the toolbox. I don't see it, as was alluded to, in 5 years, even probably 10 years, at replacing some of those really high rate production things.
I think there's exceptions to the rule. It depends on the product, and if it's an entirely new type of product. Align Technology was really a pioneer who came up with these aligners, dental aligners, and really, Additive was the only way to produce a unique set of aligners, each one being different. And I think to some extent, the hearing aid industry, same thing is true. It really checked all the boxes in terms of small, complex, expensive products, and to do it the old way was just so expensive, and not the quality was always a problem too, back in the old days of making hearing aid shells. Another might be, and I don't know enough about it, but I was talking with an owner of a company in Canada earlier this week, and I shared this with you, Doug, that it is producing 200,000 nasal swabs weekly, and they're ramping up to 500,000, and they're doing them in photopolymer on the Formlab system. They're running 110 of those machines to manufacture these nasal swabs. And there must be some, the shape, the geometric complexity of the swab that gives them the advantage, apparently. So, but that's a fairly high volume. 200,000 of anything is a lot.
Sure. And we're seeing that as well, Terry. But I think it's specialized, and it's specific times, right? There's a need. We need them now. I mean, that's another big advantage of additive that we've learned about in COVID times, right? That we all knew, right? We all knew we could respond quickly. But we've responded way faster than we've had to before. At Avid, we designed a face shield frame. I'll show you some. So this is the face shield that a finished one, And this is a frame that prints. Has DFAM all over, right? Prints very small and tiny, and then it expands into a 3D shape. When I open it up, it's got a headband integrated into it, and we're printing. There's millions of these being printed all over the world right now. And would that normally go that way? Yeah, maybe not. But in the past, not. But now, because the need is so great, and it is economical at the same time, maybe not the same as an injection molded part would be, but because of DFAM and because of the capabilities of the technologies and the network of printers out there that we can use to print these, we can make 1 million of them and really make a difference.
That's a great example. Very, very good. Here's a question at the top. What kind of impact does print failure have on the bottom line? So I suppose you could look at it if you're printing a couple of parts, that's one thing. If you're printing an entire batch of parts that maybe packed in 200 or 500 parts, I don't know how many of those face shield.
We can get 300 of those in a build.
Yeah, so if you have a failure, that's not something that doesn't make your day, right?
It doesn't. Powder bed fusion's an interesting space though, right? Because they're layered throughout the build. And so it all depends how high through the build you get before you have a failure. So you still get the parts that are underneath that failure that are probably good, right? So you don't lose everything, which is beneficial for sure. But yeah, it's no fun. And in our case, it's the economics mostly are from a downtime and labor perspective, and an uptime issue. The technologies that we're working with, the companies that we're working with, HP in particular, has done a really good job of putting some programs in place where print failure is less of an issue for the manufacturer, because they have some 3DOS systems and some ways to make that not as much of a risk just to me and our company. But at the same time, it's still an issue. So I think with all technologies, traditional or additive, it really comes down to preventative maintenance. It comes down to keeping your equipment clean. It comes down to staying on top of the equipment from a maintenance perspective to ensure that you reduce that as much as possible.
Yeah.
But it's no fun when it happens.
Yeah.
It's same when you look at high volume manufacturing. I mean, we've printed over 1 million pairs right now of our midsoles. Not exactly same types, but if you count all together, we're printing one pair basically in one go. But even then, since we have so many machines running in parallel, we're basically breaking down print failure, which is a very general term. We break it down into kind of subsets. What was the reason of that print failure? And then we're working very closely with our contract manufacturer and also Carbon, the machine manufacturer, if we do see that there is a specific failure accumulating over time. Because obviously every print failure is costly, and we need to basically eliminate that as soon as we see that it is accumulating. Of course, you can't prevent it if it happens once. It's just in regular production. But if we do see that there is an accumulation on a specific day, for example, then that's immediately looked at in order to rule that out.
Yeah, I think that's a good point, Marco, too. It depends what you mean by print failure. Is it that the machine stopped printing and you lost the build? Yeah, that's no fun. But there's also obviously print failures when it did complete and something happened either with material or the process or that. And that's almost more of a QC aspect where you have to have programs in place to ensure that you're checking your parts properly, you're testing your parts properly mechanically, so there's definitely different modes of failure depending on what you're looking. And the economics are different on those depending on when you find that failure. If parts got out to the field, that's no different than traditional manufacturing. You have to stay on top of that kind of thing.
Stephen, do you want to comment on metals?
Yeah,
that's a whole other level. It's running, let's say, several days, maybe even a week, and then you have a failure. That's even less fun.
Yeah, when you start talking metal builds, obviously first of all, it can be a lot more expensive, especially if you're using a more exotic alloy that has a pretty high cost per pound. Then any failure really can hurt the bottom line. Another part of it, though, is if you're really doing more of a low rate production, then that starts to increase the cost. And we've also seen, just discouragement. So somebody's first foray into building an additive part, they're very excited about the design they've come up with, and maybe they didn't quite get all the rules right, and then they have a build failure in the first build, and they might not be quite as inclined to try it again the next time. But most people will keep trying, and they'll learn from the build failures, but I think that's another place we do see it, is that the technology is still gaining traction, at least in the metals world, for people to consider.
This question is from David. Some of the other questions I asked, they were not named, but I know this David. He's in South Africa. In fact, I visited his facility a couple of years ago, and he asks, what are your go-to techniques and strategies to develop a customer's application into a great AM application? So what are your go-to techniques and strategies to develop a great application?
From our perspective, I think it depends on the customer a lot, and if they have any experience with additive, or are they mostly coming to it from a traditional manufacturing perspective. And that really starts with expectations, because it's going to be a different type of part than they're used to if they're used to traditional manufacturing. And so setting up some expectations as to what reality is for surface finish and all of the components with any additive is traditionally different than a traditional manufacturing method. So I think that's a good starting spot. And then working your way into it, I think one of the easy places to start is surface textures. We're doing a lot of that. We've recently added end topology to our toolbox last year. And so, we're using that tool to, I'll say, with the surface texture component, at least hide the sins of 3D printing, right? The layer lines and all of that kind of thing that we all accept as part of the process. A customer's may not have that same expectation and accept that. So finding ways around that to really take advantage of the technology and meet those expectations that you set, I think is really important. So I think it depends on the project a lot and where the customer is coming from.
I think we've seen it be more successful when somebody comes in with a little bit of an idea of what they're trying to accomplish with additive. And if people come and just say, "Hey, make this part, I heard additive's great. Make this part for me, additive." It really starts with educating them more about what are the benefits of additive and what could they possibly achieve. And once we kind of figure out, is it trying to save weight? Is it trying to improve performance? And in what way? Then I think we have a lot more success and have a little bit more tailorable strategies.
Yeah, I'd second that. I think the identification of the benefit, if it is a cost benefit or if it is a performance benefit or an individualization benefit, I think you don't do a great AM application for a customer because it is AM. I mean, in the end, the process, it's the product and the function that counts in the end, or the cost that counts. It's not that it's made with AM. So I think we would have to look first into what the end product is giving as a benefit, and then you can make it into a great AM application. But first and foremost, it needs to be efficient in AM.
Yeah, that's a great point, Marco. At the end of the day, it's a product, and you're going to use whatever technology makes the most sense. And with AM, I think one of the dirty little secrets is it's usually not just a print, right? There's absolutely the print and the right technology and the right design with that, but then there's all of the post-processing and finishing that goes along with it to make it a product. And understanding what that adds to the bottom line, the economics, how do you get there? What technologies to use to get there? I think is really important. And I think we've seen a big uptick in the AM industry of companies that are really focusing on post-processing, on smoothing parts, or tumbling and more rapid blasting, or flexible coatings, or whatever. I think it's just it's really driving that part of the industry, because at the end of the day, it's a product.
Doug, you bring up a good, or Stephen, were you going to say something? Okay, you bring up a good point about all the post processing, and from a design standpoint, what can be done, if anything, to reduce support is a necessary evil for most parts. Fortunately, in a polymer powder bed system, the powder is not typically attached to it can be caked tightly within, different cracks and holes and so forth. But in metals, it's physically attached, it's welded to the part and then welded to the build plate. And that's a whole another level of consideration. But what can be done from a design standpoint to reduce or maybe even eliminate the need for support material? Of course, it depends on the design, but can it be done?
Oh, it's huge, and it makes a big difference. I definitely want to hear what Stephen says about metals, because that's a whole nother monster than what we deal with. But even in powder bed fusion, I mean, you have to be able to get the powder out, right? So, deep holes or pathways that you need to be able to clean out, for a fluid channel or something like that. You have to plan that and test it to make sure that you can get all of that powder out and have a approach for that. Or if you have a hinge, or if you have a different component that makes it challenging to post-process. And I mean, a good example, I go back to this, our frame again. When we've redesigned this a few times, and the latest design, it prints all as one component, but when we print it now, we actually removed the back strap from the part, but it's printed all at the same time. But that allowed us to make it way easier to post-process in our automated blasting system. And you have to think ahead. Another thing that we did, one of our engineers came up with this little hook that hooks it open, so that we can now put 100 of those in our automated blaster, and they're done in 20 minutes. Versus if it doesn't have that and it's like this, you just can't get the powder out, and then we break that off and it's finished. So absolutely, using DFAM techniques focused on the post-processing requirements, I think, is really important. I'm sure in metals, probably even further along than polymers many times.
Yeah, on the metal side, it is even more important in a lot of ways. Orientation of the part, obviously plays a large factor, and the metals have a much higher processing temperatures, right? So you get a lot more residual stress and distortion potential. But orienting the parts to avoid support materials, rethinking downstream about the features themselves. If certain shapes or cross sections don't print as well as other shapes and cross sections. And so if you can do more of something a teardrop shape instead of a circular shape, it might actually reduce post-processing in the support materials and channels significantly. And thinking about how you're going to post-process the part, Doug's example is great. And you might be able to print in certain features that you can use to hold on to, you can use for positioning the part, use for inspections. There's lots of things like that can be multifunctional kind of supports and other purposes within the metal parts.
I want to grab something. I'll be right back.
So support structures in photopolymers are actually also a really big pain point from a removal perspective, and they can add a significant cost factor as well in overall part cost. If you have, and that comes to the example you mentioned earlier, if you have like non-flexible materials, it's kind of like a zipper. You can pull it and then it goes off. But if you have elastomeric materials like we're using, unfortunately, when you're pulled, it can break anywhere, and that makes it a bit unpredictable. So you were asking, Terry, hey, is it possible to remove them completely? My personal opinion is only if you are able to eliminate them completely, you can really create a cost-efficient part at this point in time. Because that is just a very, very significant kind of cost factor in the post-process if you still do have to remove them at scale. I'm talking about scale now.
This is an example metal part done on a metal powder bed fusion system. 0 supports, only to attach to the build plate. Cut it off and you're done. Well, there may be some surface treatment, of course, powder removal, but no supports whatsoever. And if I can hold it up here, do you see what attaches? There's the elliptical holes there, and also there's some what would otherwise be supports here. So everything's done in a way that rather than using support structures and material, you turn it into a feature and it becomes a part of the product. And so, Doug, you'll recognize this design. Sure. We do something similar to this in our design for AM courses, our hands-on training. And what this is it's a still to make alcohol. which, by the way, we don't condone that here in Colorado. In fact, it's illegal in the state of Colorado to make alcohol. Other things are legal, but not, you cannot do this. So we call it a water purifier. And so, but even inside where you see these coils, what otherwise would be support material that would separate in the coils or support the build, because without metal between that, the heat would cause distortion of the coils and other features. And so there needs to be material in there. So instead of using support material inside there, you just use walls to connect the coils together. And so there's tricks like that. It's like, think about how I can turn what otherwise would be support material that then I need to cut away and finish. Maybe I can just add a feature in there. And so that's worked quite effectively for certain types of parts. Not all, but certain. This is done by our associate consultant, Olaf Deagle. It's a nice little set, an executive set for people in Sweden. He was in Sweden at the time. So yeah, that's an example. All right, next question is, this is from Prabir. And he asks, how is the industry taking advantage of designing with part consolidation? So that what he means by that, I think, is to consolidate two or more parts into one or fewer parts digitally and then print those. So you reduce a lot of things, including part numbers. So what is that thinking really popular? I mean, is it taken hold among companies? Do they understand the value of doing that? And then what are the challenges around part consolidation?
I think, yeah, absolutely. That's one of the most valuable parts of additive manufacturing. I think if you were to try to sum up a top 5 of things that you can benefit from additive, it's that consolidation and the ability to redesign multiple parts as one part. You're going to do a lot of mass savings that way and production cost savings that way. So if you're not doing that, you're probably not thinking about your product hard enough.
Yeah, I agree. I think going back to our face shield frame again. I mean, when we first designed that, elastic was hard to come by, right? It was just for masks or for frames, the elastic that would hold it on your head, that disappeared quickly from the supply chain. And so to be able to design that as part of the part, one, made it something else you didn't have to source, something that came with the product as it came out of the printer, and at the time it was a necessary item just because you couldn't get it. It's obviously a strange thing with COVID, but certainly an aspect. We also have some customers of ours that have done a great job designing a spray nozzle type device with ports and channels, and they took probably 15 components and turned it into one, and yeah, the economics drive that, and it makes a lot of sense. So I think people are absolutely taking advantage of it, and you need to think about that early on because it is a big driver for the economics of additive.
The exercise of part consolidation is very manual, and it's driven with standard CAD tools. I've always wondered if it would be possible to come up with a tool that would attempt to do maybe not 100% of that consolidation for you, but even if it did a percentage of it, and it would look at adjacent parts of like material or materials that could be the same, and to consolidate them and to give you a first pass. Are any of you aware of anything like that that's under development or maybe nearing commercialization?
Nothing that we've dealt with for sure. It's always been a traditional design tool used to work through that.
Well, I agree with Stephen. I think that's definitely the top, near the top for me, as far as what can be done to really take advantage of additive manufacturing from a production sense, as to how can we reduce the number of parts in this mechanism or product. And so I would urge the inventors and entrepreneurs out there to, and especially the software people, to look at ways in which you might be able to do that. Sometimes people think they have to, it has to complete the entire task, but even if it reduces the effort by, 25% or maybe more, that would be great. Does generative shape design and topology optimized solutions essentially resolve risks involved in printing in build crashes? How do I eliminate risks, especially in metal powder bed fusion? So does generative shape design and topology optimized solutions essentially resolve risks involved in build crashes?
I don't think it really resolves the risks involved in build crashes. I think in some ways topology optimized designs can be more challenging and complex to try to build successfully. It really depends on what the outcome is. Sometimes the ligaments can be a little easier to build, right? If they're at that sort of non-supporting material build angles and you can actually produce them quickly and easily, that might reduce some of your risks. But then if you have some thinner features or cellular lattice type structures, then it may be even harder to build. So I don't think it's going to resolve the risk altogether.
We're making the assumption that everyone knows what generative design is and topology optimization is. You want to give a shot at defining that, Stephen?
So topology optimization, basically you start with a space of design material where any material basically could be kept, define some of your interfaces on it, where material has to stay at the end, and then you run a finite element-based, typically, code that iterates for the loads you put on it and tells you really where the quote-unquote ideal location of that material will be in 3D space.
We're using a minimal amount of material to get the job done.
Right, so it's whatever objective function you give it, whether that's to maximize stiffness or minimize weight. And there's lots of ways to set up that problem.
Yeah, I'm not aware about any solver that really tries to take into account kind of print build or crash. And I think it is also really dependent on the type of material, probably also on the process that you're implementing. So it might be a lot too specific to really capture that and algorithmically kind of enter that into code. Maybe there are individual solutions for a very specific process or product, but I'm not aware. And I'm happy to get educated. I mean, if somebody is aware about that, to understand if there is such a tool that does allow that.
Marco, oh, I'm sorry.
That's all right. I think where maybe some of the advantage might come from some of that's maybe not intended is that, it can help reduce the amount of heat per layer potentially. Certainly in photopolymer and in powder bed fusion that can be a challenge. So you can increase your part quality by reducing how much material is laid down per layer. So lattice structures and topology optimized parts, certainly have more design elements that handle that for you kind of at any orientation than a traditional design part. So I think that's a benefit. And then, I think where some of the solutions are coming, it's not a per part design, but certainly in nesting in powder bed fusion or builds that have those requirements, there are some software tools that will help you balance that heat load throughout the print build volume. And so that can be a way to help manage that. It's not necessarily because of the topology optimization design, but it is a way to increase quality of parts and at the risk of reducing your density. So there's pros and cons always.
Marco, at Adidas, American pronunciation, obviously, are you using purely lattice structures that in-house development software, or is it commercially available software? And are you using any tools that integrate both topology optimization with lattice structures?
Yeah. No, we're actually using a proprietary solution for that. Just because we were not able to find a software that did allow us to kind of create and integrate the aesthetic part as much as we wanted to. I think a lot of the software solutions, when we started the whole program, we're really focused on either parametrics or mechanical design, where nobody cared for what reason on the aesthetics of the lattices that were generated, or they were kind of organic, but more for kind of body parts, so orthotics, where it needs to be organic, but again, you don't care how your orthotics looks once it's inside your body. So we are actually working with our own solution. And from a lattice perspective, we took quite a while to generate a whole library of lattices. We tested them basically both virtually and physically for their individual characteristics and performances, and then selected basically those lattices out of that huge library to integrate them into our designs, where we knew we'll get the performance that we require for them, we get the functional benefit out of those, and we have printability with them. But as of now, we're not using a commercially available solution.
Regarding lattices, how do you inspect? Now, I suppose if it's a shoe, if there's a small flaw deep inside the midsole, it's not that important. But if it's an aerospace part, metal part, I'm sure Steven's team would like to ensure that everything is built to 100% integrity. Can you guys comment on inspecting parts that have very deep lattices?
Yeah, I think high quality inspection of lattice structures is one of the biggest inhibitors to actually using it in aerospace. Even establishing the right inspection routines, improving them out as high reliability for basic shapes, prismatic shapes, and bark and ligament type shapes. Still have some research and ways to go before that's even fully proven out for structurally critical type parts. So start talking about lattices, there's sort of that next level of inspection difficulty. So yeah, I think there's a lot of research that still needs to happen there before that's really proven out.
So it's been a deterrent to using lattices for lightweighting?
Yeah, or just using lattices in applications where the inspection really is highly important. If the inspection isn't as important, the application isn't all that critical, then lattices may serve more purpose there.
But you're actually raising quite a good point. In lattices, you really don't necessarily see failures from the beginning because they can be very far within a part. So during development and specifically durability testing, we're actually using CT, computer tomography, to inspect products after heavy use and to understand the performance and quality characteristics. And only if they are basically passing that, they would go into a commercial stage.
I think in the polymer world, and especially and if we're talking about DFAM and lattice structures and topology optimization, I think the elastomeric materials, like what Marco and his team is using in the midsoles, and in what we're working with the TPUs, like from Lubersol, that's where I think the real advantage comes from DFAM from a polymer standpoint, because you can really affect the mechanics of the materials. On a hard plastic, yeah, there's some advantages there, but not a lot. You're not going to get a lot of lightweighting from a nylon part. But from a elastomeric part, a TPU, you can change that kind of virtual durometer, right? You can change the stiffness, the relative stiffness throughout the part, and have it soft over here and hard over here, and you can do a lot of really cool design things when it comes to the TPUs and the elastomeric materials.
This question comes from Fernando. It's not specific to DFAM, but it's still interesting. It got a lot of votes. So, how big is the gap between a hobby grade, we'll call it a low-cost desktop system, versus a high-end industrial piece of equipment? And what are the key factors to make a decision between each price level? So what's the gap? What's the big difference or differences between a low-cost machine versus a high-end? And what are the key factors to consider when trying to choose between one versus another?
Marco, go ahead. Why don't you jump in?
I think I just accidentally unmuted myself. I was thinking about an answer. I'm obviously not super adept to hobby grade equipment, so I don't feel I'm the best person kind of to comment on that. But when we were investigating SLS, and at that time the commercial machines were really expensive, and it was just basically coming about that also we saw machines like sub $10,000 that worked with laser sintering. And we did see that just from a accuracy perspective, both of the alignment, of temperature hold, it is just becoming a bit more tricky, specifically when you have very tight boundary conditions with a hobby grade printer. So when you are working really on the boundary of a performance of a product, I think it is you have to work with a really commercial product if probably what you are expecting to get out isn't necessarily or you have a wide range of what you can accept from a quality perspective. Maybe then a hobby grade would also work. But again, I'm not an expert in fully being aware how hobby grade evolved over time.
Yeah, I think it depends on what your outcome needs to be, and and that can be quality, that can be how many parts you need to make, it could be the economics of it, materials, support, all of that kind of thing. I think really plays into what level of printer you're going to choose to go with. And so I think it really depends on your business case. What is your desired result? Is it in an engineering office and you need some prototypes that you can quickly iterate on? Maybe a lower end industrial or a higher end consumer type printer might work really well. If you're going to need to make hundreds of thousands of parts over time, then you're definitely moving into that industrial space where you need to have reliability. You need to have support from the company that makes the printer, so that when there are issues, they're there as a partner to work through those. And really it's manufacturing in a space where you're going to make a lot of products. If you think about it from a traditional standpoint, are you using a CNC Bridgeport machine, or you're using a small desktop, mill, and on some level they're both great, and it all depends what you're trying to do.
Yeah, it's a little bit like comparing a bicycle and a Ferrari. You can get across the state of Colorado on both, but it's going to be the experience is going to be quite different. Sure. In terms of speed and quality and so forth. Here's a question around simulation. How is simulation being used in Dfam?
Yeah, I think it's just sort of starting to be used, really. I think there's a lot of untapped potential there. We've done a lot of investigation of the various process simulation tools that are out there. And we definitely see them being driven more by analysts more so than designers in a lot of ways. But I think when the tools are better connected, we'll really start to see simulation start to increase the producibility of the parts that are designed for additive. The question earlier about topology optimization and helping with producibility, I think the process simulation tools are really the things that are going to start to increase producibility, especially for metal parts.
Stephen, can you name some of the top simulation tools that you have experience with?
The tools?
Yeah, that's right.
Yeah, so the MSC SimiFact tools are pretty powerful and really production oriented. Some of the ANSYS simulation tools, Siemens simulation tools, and pretty much all the major software players at this point are developing solutions, and they're all fairly productive and pretty strong. The same thing with the design for additive tools as well on the CAD perspective.
What was that, Stephen?
Same thing with the CAD tools perspective as well. If there's a major CAD package you're using, the developers probably already implemented a lot of design for additive enhancements and has a lot in work. So running out of the tool may not be necessary.
Yeah, it's good to see them integrate them into a CAD environment. So you're not moving in and out from one environment to another. You're all integrated. At least that's the goal.
Yeah, absolutely. That's huge from a design perspective, from the engineer working on the file, and not only just from designing it initially, but for rev changes later on, right? So if you're designing in your traditional CAD tool, and then you have to go outside of that to apply your Dfam components to it, whatever that might be. And of course, all of us as engineers and designers, once we do it once, we're done, right? Absolutely. So the odd chance that you have to go back and change it, like every product that we've all ever worked on, now you have to go back through that process again, right? You have to go back to your CAD tool and then redo those simulations. So either integration into the CAD tools, or having tools as part of a way to not have to redo all of that work again, I think is critical, because we all know that Rev A isn't where you end up.
You need a bottleneck. Pradeep asks, what are the key bottlenecks in simulations? Is time just running the simulation? Is that largely overcome by compute speed, or is still a consideration? Stephen, you're going to say something.
Yeah, time is definitely a big factor, right? Especially because you always want a better answer in a simulation, and you can really, drive these simulation tools for weeks if you wanted to. They aren't always fast. So, but we are finding that they are fast enough for at least predicting general, distortion, residual stress kind of issues in builds, and how things might have blade crashes, for example. Trying to get, high fidelity microstructural simulations at a part scale. Just say we're not quite there yet, but people are working on it.
Any simulation at Additive, Marco?
Yeah, actually simulation is super important for us because we are working with elastomer materials and lattices. There's basically zero experience in the industry with lattices. They were basically coming 4 years ago, where we were really starting to look into that into more detail, also from a simulation perspective. And with elastomers, you are very quickly going into nonlinear simulation. So where a lattice is bending so much that you can't just apply simple mechanics, but where there's a lot of different kind of solvers that need to be implemented. So it's becoming very, very complex very quickly. And in the beginning, time actually was the biggest enemy, because those simulations were so complex. In the beginning, we just had to work with kind of individual beams or point-to-point connections just to get to a certain point where we were kind of understanding lattices in the context of footwear first. Now I think we're becoming more and more advanced, that we are doing kind of one-to-one simulation with the real geometries, but the time factor and the cost of that simulation really plays a big role, specifically in those very complex geometries like lattices, where you really have hundreds of thousands of kind of triangles and cells that need to be solved.
This question comes from Abner, and he asks, does AM use less labor? And does AM require more skilled engineers and operators?
I think it's just different. There's absolutely labor involved in AM. Every technology, from removing supports from a photopolymer to blasting and post-processing parts for powder bed fusion, or removing metal supports, right? There's labor involved in all of that, and there's upfront labor as well, from the engineering designing parts to nesting or preparing the files for print. And so if you compare that to injection molding or something like that, it's a different kind of labor, and there might be a different cost per part for labor. But it all depends how you're taking advantage of those parts and using the Dfam components to make that economical. I think the other part of that question is it a shorter production process? It depends what you mean by that. Obviously, bridge tooling is a term we use a lot in AM manufacturing, in that a customer might eventually move to an injection mold tool because it makes sense for their economics and for their product or whatever. But AM can play a part because we can make it now, and we can bridge that gap for the next 12 weeks while the tool's ramping up and moving through those iterations of development.
Yeah, I think from a development perspective, you're definitely requiring more labor. I mean, if you're thinking about an injection process, you can go to a shop next door and they know exactly. They have been doing this for 10 years or more. They know what they do, and they know the processes. And I think for AM, just because it's such a new domain in a way to design and to manufacture, you do need more work, because like we mentioned before, simulation, topology optimization, all that is kind of a different aspect that wasn't necessarily required for an injection molded part, but now it basically is required in a design aspect from a development perspective.
Marco, can you comment on the level of automation you've developed to support your designs?
I mean, we probably started like every new technology, where you're trying to scale up and getting it work, and obviously we used a lot of manual labor to get stuff worked. The printing process, I think Doug mentioned that earlier, works quite automated, but there's also a lot of post processes required, not only the printing process itself to come to your final part, but as you scale up, it's inevitable that you are automating. So over time, we have established quite a nice and automated process, where we, of course, are automating stuff that makes sense to automate. So you still would see manual labor, obviously, in our production line. It's not fully automated, but as you scale up, it just becomes inevitable that you are automating what makes sense. And I think the major part of the major potential in automation actually is in the post process. It's not in the printing.
Stephen, Peter asked, does a subtractive knowledge, turning, milling, grinding, and so forth, does subtractive knowledge complement Dfam? And if so, can you relate some specific examples? When I first read that question, I thought he meant subtractive in general. In other words, there's a milling machine sitting off to the side, complement presumably metal parts. Yes, it absolutely does. But now I think he's asking, does the knowledge of running these machines complement Dfam, the design for additive manufacturing?
I think it does in some ways, and it actually inhibits it in others. Right? So if you take somebody that's got decades of experience doing subtractive design, that's really the mindset that they operate in. And so they're going to be really good at the back end of the additive manufacturing, the product processing, the post-processing, and understanding, what it's going to take to do the final machining or on a metal part, for example, or finishing to get that end product to the customer most efficiently. And they may have great insight into thinking of unique features that they could add onto the part to facilitate that process. But then when it comes to using things like topology optimization or generative design, the mindset of thinking of additive is a little bit harder to instill to somebody that's got all those skills in doing subtractive design.
This is an interesting question, though, also not directly related to Dfam, but Fernando asks, what are the key decision points between selecting AIM equipment with proprietary material cartridges and tanks versus the open source, meaning, of course, you can buy it anywhere. Like most manufacturing equipment today, if you're injection molding something, you can buy the material anywhere. I'm sure we all have opinions about this. Who would like to go first?
I have a pretty strong opinion about this, and I think it's a balance. I think there's some manufacturers out there that are moving towards more what I would call open platform. So it's not open source and it's not proprietary. And this is definitely more in the industrial space, where they're working with the large chemical companies and manufacturers out there to develop, work with those manufacturers to develop materials for those platforms. But anybody who has the capability to play in that space can. So I think we're seeing a lot of development in new materials, in particular in the multi-jet fusion space. We're seeing some amazing TPUs and polypropylenes and other stuff coming down the pipeline that if it was proprietary, we wouldn't be there. If it was completely open source on a system like that, you would have a lot of challenges from a warranty and from a quality standpoint. So I think in the industrial spaces, I think it's going to be a balance for a long time, is my opinion.
Mm-hmm.
I think it's a trade-off between cost and availability. Obviously, open source is preferred from a cost perspective. If it's open source, you have multiple suppliers. This will have an effect on cost down. Whereas if you need a specific material or a specific performance for your product that is not available in open source materials, you have identified basically one manufacturer that offers a very specific material type that you need for your product. I think there's there's no way around that. But obviously, non-proprietary cartridges or tanks, from my perspective, from a user of AM equipment perspective, is preferred because it has a significant price down, a significant aspect of price down that you would probably not have with a proprietary solution.
In 10 years, will we have systems that are totally proprietary, or will they have run their course and could not compete with those that are wide open?
It's a good question. I think definitely material companies are kind of jumping in that space. They are basically seeing. I'm speaking about the elastomeric field. They do see, hey, that there's a large opportunity now, so they are trying basically to enter that field. I think it depends on a whole other range of things, like the patent portfolio that someone has, if you can enter or you can't enter, or the benefit you have right now being 2 or 3 years ahead from a chemical perspective. If you maintain that and continue basically to stay ahead of that, then I think maybe it looks the same in 10 years. But I think there's a lot more focus on the elastomeric field of materials now than it was probably 4 years ago. So the competitive field might change there.
Doug, you made the point of having the system manufacturer involved in the development of the material to ensure quality and that it works well. But can you imagine you own an expensive CNC milling machine, and the machine maker says, no, you have to buy the steel from us, or whatever it is that the aluminum, you have to buy it from us because we want to ensure good quality parts off of this machine.
Sure.
Just wouldn't happen. So I mean, I'm just wondering if at some point in the future that it's like they have to let go. And
yeah, so, I'm sure as we look down the road a ways, we're going to move in that direction, right? Obviously, it's a different monster than a CNC machine in that there's a lot of the technology that's based around both the material and the equipment that's processing it. So I think you're right, Terry. I think we're going to get there, but I think it's a transition, and I think that's where a lot of this started off as proprietary over the years. It's moved. It kind of made a jump to some open source in the material extrusion space, and in some of the photopolymer. And then I think you're going to see the chemical companies working directly with the manufacturers to really make some really high-end materials that work really well in the systems. And that's going to be that open platform that's going to move towards open source someday in the future. But obviously this industry is growing at such a rapid space. It's getting the attention of the big chemical companies, right? You see the Lubrisols, the BASFs, the Henkels, the Evonik. All those companies are jumping in, not just for fun. There's an economic reason that they're doing it, and there's a future there for these companies developing these materials. And that's just going to make the users of additive give us a lot more options. One, to be able to design products with those materials, and then have more of those materials on more platforms. So
this is an interesting question from Sharon. She says, she asks, can you comment on designing and features like cleanability, security, fatigue checking, repairability, recyclability? So designing features into the part or product that would allow you to check these things. Security is a big one, especially in aerospace, but I think across the board, counterfeiting, Marco, and any product you don't want, you want it to be genuine.
Yeah. Maybe if I pick cleanability, I would say that is probably kind of removing of excess resin. That counts for me as printability. That 100% needs to be done because it's part of the post process, which would like to kind of reduce as much as possible. So we definitely design for that. Not necessarily features, but we just need to make sure that the part, as great as it looks for a consumer outside, from the inside basically is able to be powder removed or liquid removed as what we need to be doing here. From a security perspective, I think we have other means of securing genuinity of our products. And the other parts, fatigue checking, repairability, at this point in time, not so much. But I think it's an excellent point to raise that we can look at in the future.
Yeah, I definitely agree. Cleanability is by far the most important one that we look at as well. I think the other ones are coming, and people are working on technologies to add security to components, and we're learning more about that all the time. I wouldn't say it's being used very widespread yet. And I think the other components on there, yeah, excellent ideas, and we'll see where it goes, but I don't think they're very widespread at this point.
Yeah, I agree with Doug. I think we're going to see later on, repairability, recyclability, as AM starts to get a lot more implementation and more decades of experience under its belt. I think those things will be much more important. But right now, I don't see very much widespread adoption either.
What percentage of commercial 3D printed parts take advantage of Dfam?
Wow.
Yeah. Do you have a guess? Is there a difference between metals and polymers?
I mean, the level of Dfam that's applied, I think, is more the question. Right? I think everybody's going to do some minimal amount, but truly taking advantage of, I think it's a fairly low percentage. I guess less than 25%.
Of all parts 3D printed, or of series manufactured parts?
Of parts that are 3D printed, that are truly leveraging the bounds of the possible with additive.
Yeah, it'd be well under 25%.
Yeah.
You look at all the models and prototype parts and tools that are built and so forth. Doug?
Yeah, I think it really depends. There's quite often a small feature or two that certainly have some Dfam principles applied to it. I think when we start to see more production parts, that's where we take a closer look at it for sure, because we want to make sure we're taking full advantage of the technology. So I think when we have customers coming to us with production parts, and they say we want 5,000 of these, well, we're going to take a closer look at that than if they want 2, because the economic drivers of adding Dfam components to it to either save cost, make it more print better, or nest better, or whatever that might be, that drives that economics component substantially. So I think as we see more direction towards manufacturing with additive, I think we'll see that percentage climb greatly.
Yeah, Dfam has a cost associated to it, so it needs to pay off in the end. For just a small run of parts, I guess you wouldn't do that. But the larger the run, or maybe the more specific the requirement of that single part, then the more parts are using that.
Here's an interesting question from Fernando. He asks, it has to do with Dfam as being an activity, and then the manufacturing of those parts. Are they completely separate roles, or are they integrated? In other words, do the manufacturing people integrate with the design people? And how closely, if they interact, to what degree?
Sure. At Avid, there's a pretty close interaction where, I think our engineers that are applying the Dfam principles to designs and components and products, they certainly have a good handle of the manufacturability with the technologies that we use. But at the same time, they will reach out to the manufacturing and operations folks to check and review and how does this part nest? What if I did this? And so I think there's definitely some interaction. But at the same time, I think the designers need to really, like any operation, if you're going to design a sheet metal part, you need to understand sheet metal. And if you're going to design a plastic injection mold part, same thing. If you're going to design a part for multi-jet fusion or or whatever technology it's going to be, you have to really understand that technology to take full advantage of it.
Yeah, you have to work very closely together. Just an example from our space is where we really have the designers and the manufacturers, or the guys working in the on the development printers, basically, very, very closely together. Just because some of the elements we try to integrate in DFAM are there's no experience. Nobody is like really aware, does that work or does that not work? So some of the elements we basically embed from a design perspective. We need to print them actually in order to understand, does it work at scale, at that speed that we're trying to establish or not? So while the roles are separate, because the domains are just too different, they need to work very, very closely together in order to be most efficient.
Yeah, I would say at least in Northrop Grumman, the roles are definitely not separate, right? Achieving any kind of production, high quality aerospace type part requires a full team effort with the designer, your analysts, with the materials and processes engineering teams, your quality teams. Everybody's involved and early on in the process to really be successful with additive.
This question is from one of us. What are in biomimicry and bio-inspired designs have always intrigued me, and I've long felt that we can learn a lot from nature and apply that, because now it's much easier to build these structures than ever. What are the biggest barriers to successfully generating bio-inspired end product designs using tools such as topology optimization?
I think as far as I've seen, really, it's the process awareness, right? So being able to account for the overhang angles, support material, and as it's being used, your ligament size constraints in your additive manufacturing process, and the post-processing downstream considerations, and all that is still working its way into the tools. So you really have somebody running the tools that accounts for the way things are loaded and the way material can be spread, but it doesn't really account for the process. And so you find the iterations in using those tools to take a lot longer than you'd really like. Especially the first time you use them, it could take somebody weeks to finally converge on a design they're happy with, just as they try to understand what's in the simulation and what's not in the simulation.
So is that why we haven't done more in this area? Because I mean, we can get inspiration from walking through a forest and seeing these trees and other types of plants, birds, insects, and so forth, and wow, we can apply that or to additive. But then you begin to reality check them when you start to begin to use these tools. They're just not as well. I don't want to put words in your mouth, but I think you said it best, Stephen. Is that really the problem?
I think that's one of the main problems. The other problem, like this you're trying to do the biomimicry, right? You see something in nature that you really enjoy, and you're like, I'm gonna go try to recreate that, right? That CAD, NURBS-based tools are really not set up to do that kind of complexity. And we are starting to see some more implicit modeling techniques with like the topology software that make those sort of exotic designs much more tractable into products. So I think we're just kind of starting to get some interesting tools out there that maybe can do that much more efficiently than you have in the past. And maybe Mark could speak to that part a little bit more in terms of the pattern design and what you can do with biomimicry.
Yeah, I think while biomimicry as a discipline in a way has been out for a while, but I think additive manufacturing really opened a whole new door to really apply that from a product perspective. But again, I think products are made when they can be a commercial success. So we don't use biomimicry because we think it's cool, but in the end, there needs to be a kind of either a commercial or a performance benefit behind it. I think where before people maybe weren't even thinking about it just because they were in their kind of world of the manufacturing process they had to adhere to, or the boundary conditions. Now I think we need to change our mind and think, hey, if there is a significant benefit I get, and in the end, the commercial benefit I get from a topology optimized part, or from a part that gives me a benefit I haven't been able to achieve in the traditional process, then this is definitely a new domain that we should think in when we think about part design. But I haven't seen too many commercial parts where I think this has been applied, which in the end probably comes down to cost, or probably it's cost.
We have about 5 minutes left, so I'd like to take the last few minutes to really focus on the future of design for additive manufacturing, really across the board, the skills or the lack thereof, the tools. If you could, dream up and have at your disposal any tool, what would it be? So dream a little bit, if you would, and what's missing, and what would you like to see in the future?
About that, to me, it's really the connection of the tools, right? It's taking the process simulation, it's taking the design for post-processing, it's taking the upfront conceptual design and laying out, your design optimization type problems, and really getting that all in one cohesive package that accounts for the process, that accounts for total cost in that development, and then streamlines it to where people can actually learn it rather readily and operate those tools. So I'd say that'd be the ideal outcome.
Okay.
Same here. Yeah, I think right now we are basically where parametric design in the mechanical space maybe was 20 years ago, where you have very many separate solutions that help you to come to your goal. But it's fantastic when I see how an engineer is working and everything is integrated in one system, and you're basically jumping without breaking the kind of even the file type. Going through the complete life cycle of that digital product. And right now, this isn't really fully possible in the AM space. So we have a lot of breakages and a lot of kind of incohesive back and forth mechanics in a way in the development process. And I think that would be a huge benefit. Also enabling DFAM for a lot more people, because right now I think this is one of the complexities why it's not so widely used, because it's just cumbersome to do it.
Yeah, I completely agree. I think the integration is huge. We all like it when we can do our parametric model in our CAD system and stay there. And yeah, exactly what Marco said. It's a great way to, especially when, like I said earlier, revisions and tweaking and back and forth and all of that. And so there's those breakages currently in the AM model, which I'm sure as the technologies mature and the companies that are developing these tools mature and consolidate, I'm sure we're going to see much more of that, just like CAD did over time. And so I think that's a big component. What I'm really excited about, I think, is the change in kind of methodology for designing. And we're seeing that as younger engineers are learning some of these tools in school and these techniques, and as they're entering the workforce, we're starting to see people thinking in a different way than when I came out of school, right? This just wasn't even a thought in our head hardly to have these types of techniques. So I wasn't trained as an engineer to think this way, but now we've learned it over time and developed these skill sets, and now as we're bringing new engineers into the fold that have those skill sets and maybe have a different perception of how manufacturing is going to be in the next 5, 10, 20 years. We're going to see wider adoption and faster adoption as both the technologies from a printing standpoint and from a software standpoint and the knowledge base kind of come together all as one.
Great. Any final comments? Any words of wisdom that you'd like to pass along to a couple hundred people now?
For getting started with your first design for additive application, really do that upfront homework to figure out what's going to make the most sense for you, what you really want to get out of it, and then reach out to somebody in industry to help out, whether that be a service bureau that does helping, or one of your customers that maybe you sell products to a larger customer that already has additive experience, and really just collaborate. Things like America Makes are great communities to engage in and participate in. So don't go it alone, I guess would be my final thoughts of wisdom there.
Yeah, I second that. I think the 3D printing industry, how I have experienced it, is like probably the most open and most friendly in a way. So yeah, I would also really second Stephen what you just mentioned. Reach out, talk to people, and I haven't had a bad experience in that space.
Yeah, I agree with that wholeheartedly. I mean, you know, we are a service bureau, and we have lots of friends in our industry that we collaborate with all of the time. That I guess in some other industries you'd consider them competitors, and I suppose they are, but we almost don't think of it that way. There's just a lot of really good collaboration, working together, and so yeah, if you're just starting this space, you know, seek knowledge, seek help. I think there's great organizations out there and companies that are always willing to give some advice and push you in the right direction. It is a great industry.
With that, used our thanks to our three panelists. A virtual applause for all of you. Thank you very much for your time and expertise. We appreciate it very much. Thanks to Link3D for sponsoring this. I see Andera here, and thanks to America Makes for sponsoring the four-part series. So the fourth one will be September 10th. It's on a Thursday, same time, same place. The focus is on the future of additive manufacturing. So we're really going to look out a ways, both in the short term, but also in the distant future. And so we're looking forward to it. So thanks again to everyone. But it's not over. We have more to come. And if you weren't able to join the first 30 minutes of networking, it's really a treat to do this. So we have these tables. Each one is labeled, some with a theme, some with a company. You can sit down to any table. You just double click on an empty chair, and then you can sit down. If all the chairs are filled, just wait for one to open up. In the meantime, go to another table, and you can have some great chats about the topic, the company, or really anything you'd like to discuss. So with that, I'll turn it back over to Andera.
Thank you, Terry. And thank you to the panelists as well. Really great panel, interesting today. Thanks for being a part of this. So before we jump back in to networking, just a few things. Aside from what Terry mentioned, make sure to turn on both your camera and microphone to get the best experience. And then also feel free to use the chat function as well to set up meetings or invite people to the table you're at too. And for those of you that are new to the Remo platform, once we're back in the networking floor, there's also a video to the left of the stage with detailed instructions on how to use Remo if you're having trouble. And for anyone that is also having issues, you can reach out to me on the direct chat and I'm happy to help. So thank you to everyone that's here today for coming. Look forward to networking.
Thank you.
Back to networking. All right.
Thank you.